Hi there. I kind of wanted to um, do some review stuff with you today. Um, Assignment 64. And this is part of our review. It says 3 worksheets in class and practice. I also thought there were stations too, so I'm not sure. But let's think of this as this is what we would have done in class. Okay. Number 1. I'm giving you a graph of f prime of x. Here it is. It's got zeros at -2. Not there. And 2. 1, 2. And we're going to bounce here. And we're going to have a max here. And we're going to have a min here. And we're going to cross here. Something like that. Okay. That goes to the max. Nice. And this is a graph of f prime. Okay, f prime. Now, what I'd like to know is all these things about f. When is f increasing? When is f decreasing? When is f concave up? When is f concave down? Can you help me find those? Okay, so take a few minutes to try this out. Remember, this is a graph of f prime, not a graph of f. And we're looking for when f is increasing or decreasing. We're also looking for when f is concave up or concave down. Welcome back. So this is a graph of f prime. F prime represents the slopes of f. I know f is increasing when f has positive slopes. The slopes of f need to be positive numbers in order for f to be increasing. So I think f is increasing on -infinity to -2, union -2, -2 to 1. Not 2, because at 2, where I have that bounce, that's a horizontal tangent. That's neither increasing nor decreasing. Okay? F decreasing, well, that's when f prime, that's when f's slopes are negative, which means f prime is negative. And so I'm going to say, hey, 1 to 3. But what's happening after 3? Well, positive y values on f prime means the slopes of f are positive after 3. So, yeah, I got more increasing here. Okay, now, what about f being concave up or concave down? Well, I can figure that out based on looking at a graph of f double prime. I've got a graph of f prime. So, there are 2 ways I can do this. One way is to say, this is a 0 slope, this is a 0 slope, this is a 0 slope. And so at each of those places, f double prime will have an x-intercept. Okay? My slopes, not the y values, the slopes on this graph are negative here. Very negative, less negative, almost 0. So I'm going there. And then my slopes are all positive here on f prime. A little positive, more positive. That's about as positive as they get, and then less and less positive until we get back to a 0 slope. So something like this. Here, I have everywhere negative slopes on f prime. A little negative, more negative. That's about as negative as they get. Less negative, almost 0, and then back to 0. So I'm going with something like that. And I have all these positive slopes on f prime here. A little positive, more positive, keep going positive. And so my red graph is f double prime. And then from my red graph, I could say, okay, f is concave up when f double prime is greater than 0. And I see f double prime is greater than 0 on -2 to -1, union 2 to infinity. And f is concave down when f double prime is less than 0, and so that's over here and here. So -infinity to -2, union -1 to 2. Fabulous. But wait, I'm wondering, is there a way for us to have done this without actually going and drawing f double prime? So here's what we can say. F is concave up if f double prime is positive. But f double prime represents the slopes of f prime. If f double prime is positive, that means the slopes on f prime are positive. The slopes on this graph are positive. Well, I have positive slopes from here to here, and I have positive slopes from here to here. What's happening on f prime where I have those positive slopes? Oh, f prime is increasing. And when would f double prime be less than 0? If f prime had negative slopes. So I see f prime having negative slopes here and here. And if the slopes of f prime are negative, that means that f prime is decreasing. So it's not just this and this, but it's also this, this, and this. I need to know all of those things, okay? I need to know that when that f will be concave up if f prime is increasing, or f double prime is greater than 0. I bring this up because there have been 2 years in the last 10 years when at the AP reading we were told, even though students had written perfectly good justifications for concave up using, well, f is concave up on this interval because f double prime is greater than 0. Yet we were told we couldn't give credit to that. Why not? Well, they said, and they've said this twice now, that we gave them a graph of f prime. And since we gave them a graph of f prime, the justification needs to be with respect to f prime. So both of these are justifications, and occasionally College Board is a little weaselly. They give us f prime, we should talk about f prime. Not always, not reliably, but sometimes. So I would say this is a better justification than that one. Okay, but traditionally, this is the one that people use. Okay. Next, how about this? I got a graph. Let's have a graph. And I want to go down and bounce and up and wiggle. Okay, so really it's a little like that, and it doesn't come under, and it goes up from there. And I got a bunch of points here. This is A, this is B, this is C, this is D, this is E, this bounce point is F, I've got G here, and I'm going with, it's interesting, it just sort of stops. I'm going to put some points over here. H, I. All right, so we've got this graph, and this is a graph of f. This is f of x, okay? Where do f and f prime have the same sign? Like f is positive and f prime is positive. F is negative and f prime is negative. Yeah, so What do you think? I see most of this graph, f is less than 0. So f is negative from here to here. Well, on that interval, are there any places where f prime is negative? Sure. Here, here, and here, here. These are places where f prime is negative because the slopes of f are negative whenever this function is decreasing. Not here. Here, my slope of f is 0. Likewise here, not here. Here, the slope of f is 0. So if I'm supposed to pick points where this is true, then I'm going to say here at B, f and f prime are less than 0. What about here? I have a negative f value. My slopes are negative. Sure. And G. Nice. And over here, f is positive, but I don't see any points here where f is positive, where f also has a positive slope labeled. So I think this is all I'm supposed to write. All right, so good. We're looking for when f and f prime have the same sign. So f prime is negative and f is negative here. Here, f is negative, but f prime is positive. F is negative, but f prime is positive. So I'm not going to include those. But these 2 points, sure. All right, what if we change this question to at what points, instead of where, at what point do f and f double prime have the same sign? Okay, well, like we said before, f is negative almost everywhere. So f double prime negative. Well, what does it mean for f double prime to be negative? F double prime negative is when f is concave down. Oh, I see f being concave down from here to here. I also see f being concave down from here to here, but I don't have a point there. In fact, I can't use these points either, because I believe these to be inflection points. Inflection points, points where f double prime is equal to 0. So not here or here, but any points from here to here, like E. E is a place where f is negative, below the x-axis, and f double prime is also negative because f double prime is negative when f is concave down. What about at this point called f? Well, yeah, so here's the thing. At this point, this function has a y value of 0. But f double prime doesn't have a value of 0 here. F double prime, because f is concave down, f double prime is negative. So no, not at that point. Only at point E can I say that. If I put a point over here, we could say it again. Or if I put a point over here, like point J, I would say f and f double prime have the same sign because f is positive, and I see concave up, f double prime is positive. So at J, because f and f double prime are both greater than 0. And where else did we say at E? At E, because both f and f double prime are less than 0. Okay, next. That's a great question we've got. What about not f and f double prime? What about f prime and f double prime? At what points do f prime and f double prime have the same sign? Well, let's think about that. I'm looking for f prime to be positive and f double prime to be positive. What does that mean is happening on F? Well, if F double prime is positive, that means that F is concave up. And if F prime is positive, that means that F is increasing. So can we identify any places where F is increasing and concave up? This is concave down. This is an inflection point. No, I need concave up. So I'm looking for increasing and concave up on this graph. So increasing and concave down, decreasing, F double prime is 0 there. Ooh, increasing and concave up at J. F prime and F double prime are greater than 0. In fact, F prime, and F double prime are all greater than 0. Well, 3. What about this one? So we're saying F is decreasing, and if we want them to have the same sign, so I want decreasing and concave down. I've got decreasing over here, but that's an inflection point. And I have decreasing over here. But I also want concave down, and this is concave up. This is increasing and concave down, so now that doesn't work. If the question had been when do they have opposite signs, I could go with this. Yeah, but right now I think I only see J. Okay, next question. How about places where F and F prime equals 0? Can you find any places where F and F prime equal 0? So F equals 0 is an x-intercept on this graph. So we're only looking here, here, or here. And F prime equals 0, those are the slopes on F. Do you see any places where the slopes on this graph are equal to 0? Well, yeah, here, I agree. But that's not also F equals 0, so no, that's not good. What about here? My slope is 0, my y value is 0. So I'm going to say at point F. Okay, do we have any others? How about here? Slope is 0, but F isn't 0. 0 is way here. So that doesn't work. Oh, I. Y equals x to the third and x equals 0. Sorry, that's a horizontal tangent. So I believe that that is F prime equal to 0, as well as F equal to 0 at points F and I. F and F prime equals 0. All right. And the last one, what if we say F double prime and F prime are equal to 0? Well, F prime is equal to 0 here, 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 and here. And F double prime equal to 0? Well, I usually think that about inflection points. Here, I change from concave to concave down. Here, I change from concave down to concave up. Here, I change from concave down to concave up, and we have a horizontal tangent to top. So, at x equals I. Okay, so I think problems like that are really good for you to do and think about. They really sort of, yeah, coach says that's a great drill. You should get comfortable with that. All right, what's next? Oh, so here. Y equals 2x plus cosine x. So I got this function, and if you like, we can call it f of x, and I want to know everything. I want to know mins and maxes. I want to know increasing and decreasing. I want to know concave up and concave down, and I want to know inflection points. And no calculator. Okay, so what do I need? Well, in order to talk about maxes and mins and increasing and decreasing on with f, I need f prime. So that's going to be 2. Derivative of cosine is minus sine. Okay. And I think I want to put a boundary on this. Shouldn't we have like 0 to 2 pi? Because otherwise this goes on forever. So let's take a look at f prime. We know that sine is never undefined, so f prime is never going to be undefined. In fact, I think I want to put that so that we actually have an endpoint. Okay. So what else can we say? Well, we can say f prime equals 0. When does f prime equal 0? When 2 minus sine x equals 0. Uh-oh. Sine x equal to 2? That never happens. We know the sine graph only goes up to 1. So no, there are no places where f prime is equal to 0. Well, that's very interesting. What happens when I do plug something into f prime, like 0? What happens? So here's my f prime, and I plug in a 0. Sine of 0 is 0. 2 minus 0 is 2. So what's going to happen is that any point I plug into f prime is going to generate a positive output. Well, that's very interesting. So I can say, because f prime is always greater than 0, f is always increasing. Okay, f is always increasing. Now, I know you're saying, but wait, Mr. Kukla, because sine sometimes is decreasing. Sure, but let's take a look at what's going on here. We've got a negative sine graph that's been shifted up 2. So here's y equals 2. And our sine graph goes, whee, because it's negative sine, it starts down. Does this negative sine graph that's been shifted up 2 ever get to the x-axis? No, it doesn't. F prime, that's what this is a graph of, f prime is always above the x-axis. F prime is always positive y values. Therefore, f is always increasing. F is always increasing, and therefore f is never decreasing. So the only places I could have maxes or mins, because f prime is never 0, and f prime is never undefined, the only places would be at the endpoints. So let's take a look what happens when we put 0 in here. Cosine of 0 is 1. 2 times 0 is 0. 0 plus 1 is 1. So we know that f of 0 equals 1. What about f of 2 pi? If I plug a 2 pi in here, the cosine of 2 pi is 1. 2 times 2 pi is 4 pi. And this is much bigger than that, so I've got a max here. You could also think about this on an f prime sine chart. Here's an f prime sine chart with 0 and 2 pi. We determine that f prime is positive everywhere. So this, and from this point, f prime is positive, therefore f is increasing, f is increasing, f is increasing. That means that this is actually a min, and this is a max. Are you comfortable writing those endpoint justifications? So let's take a look at an endpoint justification. There is a min at x equals 0 because to the right of x equals 0, f prime is greater than 0, and x equals 0 is the left endpoint. And we need to do something also for our max at the other end. At 2 pi, we'll say there is a max at x equals 0 because to the left of x, no, 2 pi. To the left of x equals 2 pi, f prime is greater than 0, and x equals 2 pi is the right endpoint. Fabulous. Okay, so don't forget justifications for all mins and maxes and inflection points. You should also be able to justify when a function is increasing or decreasing, concave up or concave down, but that's a little more standard, I think, for people. I know that f is increasing when f prime is positive. Okay. Next, we didn't talk about concavity. So f prime was 2 minus sine x, and f is 2x plus cosine x. But in order to do concavity, well, I guess I could do concavity by just looking at f prime. But really, I think it's so much easier just to find f double prime, which is negative cosine x. And take a look at negative cosine x on 0 to 2 pi. So here's our f double prime graph. And what can I know? Well, when f double prime is less than 0, f is concave down. So f is concave down on 0 to pi over 2 union 3 pi over 2 to 2 pi. And I could say f is concave up on, well, f is concave up when f double prime is greater than 0. So from here to here on, no, not equal to pi over 2, 3 pi over 2. So do we have any inflection points? Sure. At pi over 2 and at 3 pi over 2. Why are those inflection points? F has inflection points at x equals pi over 2 and x equals 3 pi over 2 because f double prime changes sign at those points. Okay, f double prime goes from negative to positive. F double prime goes from positive to negative. Those points, because we have that sign change, we know that those are going to be inflection points on f. F may be a function that's always going uphill because of this, but that doesn't mean it's not changing its concavity as it goes up, and that's the effect of this trig component. Okay, we said concave up, we said concave down, we said inflection points. Good. Yeah, so that's, when you have to sort of show all those things, that was a big reason for calculus. Because suddenly, in the age before graphing calculator, we could come up with all these qualities of a function and then graph it. We could know what it looks like. Okay. No, I promise, graphing functions isn't the only reason for calculus. And yes, there's plenty more coming after this test. Think of this, though, as one of the main uses for a long, long time. I, sometimes feel like getting the rules down for increasing, decreasing, concave up, concave down, inflection points, maxes, and mins, in addition to their justifications, that takes a while. And that's, once you've got them, and that's great. But sometimes it's the algebra that people have difficulty with. So, for example, I want everything for this function. I want to know when this function is increasing or decreasing. I want to know when this function is mins and maxes. I want to know when this function is concave up or concave down. And I want to know when it has inflection points. I will also tell you that in this situation, it is always so much more happy if we do that. So, in order to figure out increasing or decreasing and maxes and mins, I need y prime. That's the derivative of this product. So this times the derivative of that. You get x times 1/2 5 minus minus x, don't forget to subtract 1, times the derivative of that inside stuff, which is negative 1. Done? No, no, no. That was only the first half of the product rule. Now we need plus this times the derivative of that. Do you see why we were doing all that factoring that we were doing last year? Yeah, because we need to. So I'm going to factor out a 5 minus x to the negative 1 half from each of these. Okay, what's left over? Well, it's negative 1, it's 1 half, minus x. Then our plus sign. We factored a negative 1 half. So we've also got 5 minus x for the first. Well, you know, I can just do 1 and then combine like terms. Minus 1 half minus 1 is going to be minus 3 halves x plus 5. And then here, 5 minus x to the negative 1 half. Here's my y prime. Now remember, in order to find maxes and mins, I need y prime equal to 0 or y prime undefined. Check it out. This is the same as saying negative 3 halves x plus 5 over square root 5 minus x. Y prime is undefined when this denominator is equal to 0. So just by setting each of these factors equal to 0, I'm taking care of f prime equals 0 and f prime undefined. So I know f prime is going to be undefined at x equals 5. And over here, when I set this equal to 0, minus 3 halves x plus 5 equals 0, I get 3 halves x equals 5. And if I multiply by 2/3, I'm going to have 10/3. Okay, well, let's make a little f prime sign chart. Actually, I'm going to want to take this work away and put y prime equals 5 minus x to the negative 1 half minus 3 halves x plus 5. Okay, so let's build a y prime sign chart. 5 is going to be on it, and 10/3. Now, is 10/3 here or here? Well, this is 15/3, so 10/3 is over here. 10/3. Fabulous. All right, so let's think about this for a moment. What's the domain of this function? Well, remember, I can't have a negative number grabbing. So even though this can be any number I want it to be, if I plug in a 6 here, 5 minus 6, so this function doesn't exist over here. This is an endpoint. Nobody told me that. I was supposed to figure that out myself. All right. So what else can we say? Well, let's test some values in y prime. And how about 0? And how about 4? We're going to test 0 and 4 in y prime. Here's y prime. If I plug a 0 there, I've got a 5 on top. If I plug a 0 there, I have the square root of 5 on the bottom. 5 over root 5. Is that a positive number or a negative number? Well, that's a positive number. So when I plugged in 0, I got positive. What happens if I plug in a 4? Okay, 4 divided by 2 is 2. 2 times negative 3 is negative 6. Negative 6 plus 5 is negative 1 on top. On the bottom, when I plug in 4, 5 minus 4 is 1. And the square root of 1 is 1. Negative divided by positive, I've got a negative. So I know some stuff now, right? I know that f is increasing on negative infinity to 10/3 because f prime is greater than 0. And I know that f is decreasing on 10/3 to 5, endpoint, because f prime is less than 0. And I probably want to say on this interval for both of these. Okay. What about maxes and mins? Well, when f prime goes from positive to negative, that means f has gone from increasing to decreasing. We must also be passing through a slope of 0 in order to go from a positive slope to a negative slope. So I'm going to say x equals 10/3 is max. Now, do we have any mins? Well, look what's happening over here. F prime is negative, therefore f is decreasing until we get to that point. So I've got x equals 5 is a min. All right. Can you write those justifications? I know we just did them, so I'm sort of hoping that you can take care of that. Now, we've talked about increasing, decreasing. We've talked about maxes and mins. We were careful with our algebra, but now we need to do f double prime. And what do we know about f double prime? Well, this is going to give me concavity. This is going to give me inflection points. So I really want to find f double prime, which means I've got to take the derivative of this. So this, 5 minus x to the -1/2, times the derivative of this, plus this, times the derivative over here, which is going to be -1/2 x, 5 minus x to the -3/2. And don't forget to take the derivative of the inside. That's going to be a -1. And since I'm kind of out of space over here, I'm going to put the -1 here. Okay, so what can we factor? Well, I like the idea of factoring out this to the lowest power. So y double prime, we've got 5 minus x to the -3/2. I also want to take out that and that. And how about that negative? So let's factor out a -1/2. And so what's left over? Well, we factored out a -3/2 here. So that's going to be 5 minus x to the first. We factored out this, but we left the 3. So we still have a 3 here. Okay. And we took out the -1/2. We took out all of this. So all I have to worry about is minus being distributed to each of those. So plus 3/2 x minus 5. Okay, so let's tidy this up. 15 minus 3x plus 3/2 x minus 5. And that's going to be 10 minus 3/2 x times 5 minus x to the -3/2 and a -1/2. And there's y double prime. Look, that's just a stretching factor. You're welcome to set this equal to 0, but 1/2 is never going to equal 0. So, yeah, that doesn't give you any zeros on y double prime. 5 is a 0 on y double prime, and setting this equal to 0 and getting x equals 20/3 is also a 0 on y double prime. So let me write y double prime up here nice and clean, in case we want to refer to it later. -1/2, 5 minus x to the -3/2 times 10 minus 3/2 x. Okay, so let's see what we've got. We know x equals 20/3 and x equals 5. So I make my y double prime sign chart, and I put 5 on it. And where's 20/3? 20/3 is 6 2/3. 6 2/3. Okay, so I'm looking here and I'm saying, wait a minute, what was the domain of this original function? Didn't we say that we can't plug 6 in here because 5 minus 6 would be -1, and I can't take the square root of -1? So there's a restricted domain, and then 5 is actually the right endpoint. Yep, that's exactly what we said. So that stuff doesn't exist. That point certainly doesn't exist. And it is very interesting how many students will, test those intervals here and then draw the wrong conclusion. So let's see what happens when we plug in a 6. 5 minus 6 You get -1. Can I take the square root of -1? No, it doesn't work. Many students make it work. I don't know how they make it work. They just make it work. If I plug in a 6 here, I got 18 divided by 2 is 9. 10 minus 9 is 1. Sure, that's great, but not here. My function doesn't exist past 5. So y double prime looks like it's only going to have one SIGN. Let's plug in 0 and find out. So if I plug in a 0, all this goes away. I have a positive times a negative, and under the square root always has to be positive. So positive times negative, I got negative. That tells me that y is always concave down. And there are no inflection points because I don't see y prime changing from negative to positive or positive to negative. If y prime doesn't change signs, y is not going to have an inflection point. And I can't have an inflection point at an endpoint, remember? So let's take a look at our calculator and see if we can see this sort of confirmation. All right. Hello. There we go. Clear. And we've got x square root 5 minus x close parentheses. I will say that this is not necessarily a calculator problem on the AP exam. They expect you to be comfortable with this algebra, which is one of the reasons why we've spent so much time doing that algebra. So zoom standard, what do we see? This function is always concave down. Always concave down. From negative infinity up to 5. Remember, the reason there's a gap there is because we're asking the calculator to draw something that's nearly vertical. And the old calculator is not able to draw nearly vertical. So that's as best as we're getting. We know there's an x-intercept at 5 because 5 minus 5 is 0. And 0 times 5 is 0. And so y equals 0. There is an x-intercept there. What else did we say? Well, we said we'd be increasing from negative infinity up to 10/3. Let's check to see if that's 10/3. Second, calculate max. Go to the left side of that max. Go to the right side of that max. And I see 10/3. There it is, 3.333. So, nice. There's the value of my maximum. And then this one here, remember, at 5, we're going to have a min. Our sign chart was positive to 10/3, and then from 10/3 to 5, we had negative on y prime. Therefore, y prime is decreasing on that interval. Yes, and y is always concave down. Well, that's fabulous. It's great that we were able to do that. So, we need our knowledge of calculus, we need our algebra skills fairly robust, at least with factoring, to be able to get through that stuff comfortably. Let's do one on a calculator. Y equals 500 over 1 plus 10 raised to the negative 0.2x. Okay, so here's a little logistic function, and again, I'm interested in knowing when is y increasing, when is y decreasing, when is y concave up, when is y concave down, where are their inflection points, where are their maxes and mins. All right. Now, one of the things I've been talking about over the last 2 years is saying, well, let's think about this before we find y prime. And no, I don't want to do it by hand. I really want to take that this is a calculated problem and do this stuff on the calculator. But I like to think about this stuff first. First, what's a logistic curve look like? Remember, it has two horizontal asymptotes. And this number is that number. The upper horizontal asymptote, the carrying capacity of the environment, is always this number up here. And so my graph goes something like that. Okay, so tell me, what do you see? Well, I see this function is always increasing. So I'm expecting y prime to always be positive. I see this function has an inflection point. where it goes from concave up to concave down. I'm not quite sure where it is. It's somewhere around here. But I see an inflection point. I definitely see the function as concave up to that point, and the function will be concave down after that point. I don't see any mins or maxes. This continues to, these are positive slopes, positive slopes, positive slopes, positive slopes. So I know that f, or y, is always increasing, never decreasing. And because f doesn't go from increasing to decreasing, there are no maxes. And because f doesn't go from decreasing to increasing, there are no mins. This graph goes on forever, so there are no endpoints. So I got no mins, no maxes, never decreasing, always increasing, an inflection point somewhere, some concave up and some concave down. So let's talk about how we can find those things. Let's talk about using our calculus. I'll pull out my calculator, and I'll wish I had better light on it. Maybe I can hold it like that. Yeah, that's awkward. All right, so we've got our function here. Oh, no, we don't. We need 500 divided by. Remember, everything in the denominator has to be in parentheses. 10 raised to the negative 10 to 2x. Close 1, close 2. All right. By the way, you know the carrying capacity is 500, so having a y max of 10, probably not very useful. 500, 0, steps of 25, 50 might be better. And then what about x values? Well, I don't know. Negative 10 to 10 might be fine. We have a syntax error. Oh, let's go look at our syntax error. Too many? Oh yeah, I didn't put in a. Yeah, I'm going to go back over here and insert an open parentheses. Nope. So, oh, look at that. There it is. Nice. So there we go. There's our logistic function. But I want to find y prime equal to 0. Y prime. So let's make a graph of y prime. We know that we can do that by going to y2 and then math, scrolling down to end derivative. And on my older calculator, I have to type in y1, comma x, comma x. Okay? And I didn't put it in y2. Well, let's see this. Let's try again. Okay, end derivative here. And we want y1, comma x. It's always comma x here, because we don't want to know the derivative just at a point. We want to know the derivative for all points. Great. Okay, so that's f. Now what about f prime? Okay. Hey, look, it's the COVID curve. That's the COVID curve. Right? We want to flatten that COVID curve. And what is this? This is the y prime curve on our logistic model. The units here are people infected. This is total people infected. This is people per day. That's what these y values are. And we want the number of people per day to be as low as possible. Otherwise, the hospitals are completely overwhelmed. We all remember the refrigerator trucks of dead bodies in New York City. That's kind of really horrible to think about. And so one of the ways that we get around having trucks full of dead bodies is by reducing the rate at which people are getting sick. Still lots of people getting sick, but we want to reduce that rate. We really want everyone, or many people, more than 70% of people, at some time to become infected so that the rest of uh, the rest of the people have herd immunity. Um, yeah, but as we've seen with in the recent years with anti-vaccine families, uh, that 70% may actually need to be a higher number of people who can't get it in order for those people who don't want to take a vaccine to be able to safely avoid catching that illness. So, yep, we live in some interesting times. All right, so enough about this. Let's look at the graph again. Okay, and in fact, I'm distracted by this graph, so I'm going to turn it off. And I'm just going to look at this derivative. In fact, the y value on the derivative function is much lower. So I think I'm only going to go to 50 instead of 500. Okay, so now it's graphing the derivative of this logistic curve. Oh, so close with 50. And back down again. And believe it or not, upward. This kind of looks like always concave up on f prime, but we see here concave up, concave down, concave up. And I'll see that if I change my viewing window to go, say, go to 7. It does take longer because our calculator is actually finding the derivative at, many points using that original logistic function. Okay. Fabulous. So here's my f prime graph, and this is the line y equals 0. Down here at the bottom. Does f prime ever go to 0? No, it gets close to 0, it gets close to 0, but never equal to 0. So my y prime sign chart is going to be plus. That's it. There are no critical points. Y prime is never 0. Y prime is never undefined. There are no endpoints. So that's what I got. What about y double prime? Well, again, I can have my calculator help me with that. I'll turn off this one now also. And I want the derivative of not y1, but y2. Okay. Comma x, comma x. And now, though, there's a problem with the graph, and I'm wondering if you know what it is. Look, it looks like y prime is going to 0 here. And then I don't see anymore. So remember this y prime graph we had, this COVID curve? Y prime is increasing, so y double prime is positive. Y prime is decreasing, so y double prime is negative. I haven't left any y value space for y double prime to go negative. And I definitely don't need to go up to 75 anymore. So how about we say 10, but we also allow for negative 10. Let's see what that does. Okay, tink at 0, and then back up again. Back up again, there it is. And so my y double prime sign chart definitely has a 0 at 0. I'm approaching 0 here, I'm approaching 0 here, but I'm never going to get to 0 on these ends. So I've only got one critical point on y double prime. And to the left of 0, I see plus. To the right of 0, I see minus. See how we change sign from positive to negative at x equals 0? Well, what does that tell me about y prime? A double prime. I'm sorry, what does that tell me about y? When y double prime goes from positive to negative, we know we have an inflection point. All right, so let's write up all the stuff we know. 1. We know no max or min because y prime is never equal to 0 or undefined, and there are no endpoints. We can say y is increasing on negative infinity to infinity because we saw that y prime was greater than 0 on negative infinity to infinity. Y prime is never decreasing because y is never decreasing because y prime is never less than 0. What about inflection points? We have inflection point on y at x equals 0 because y double prime changes sign at x equals 0. We also know y is concave up on negative infinity to 0 because y double prime is greater than 0 on negative infinity to 0. And finally, we know that y is concave down on 0 to infinity because y double prime is less than 0 on 0 to infinity. Right. Do you understand why I said we need to get in the habit of writing a sentence with every answer? Because when we've gotten this far and have actually been writing sentences, it is not hard for our brains to continue to write sentences. And we got a lot of sentences to write here. All right, so you need to be able to do this max, min, increasing, decreasing, concave up, concave down, inflection points thing by hand and on the calculator. So please make sure you know how to do those things. Additionally, hold on, we haven't even talked about MVT yet. So y equals x squared minus 3x plus 1 on 1 to 7. And what I'd like to know is, A, does y meet the preconditions for MVT? And in order for us to answer that question, we have to know what the preconditions are. So do you remember that if statement? If f is continuous on a to b and differentiable on a to b, not worried about the derivatives at the endpoints, then, okay, so these are my preconditions. So let's look at this. This is a parabola. We know a parabola exists from negative infinity to infinity, so certainly our parabola is going to exist from 1 to 7. Good. I know that this is continuous. And what about differentiable? Well, I know the derivative here is going to be 2x minus 3, and that's a linear equation, and that exists everywhere, and it's certainly going to exist on 1 to 7. So I know that the derivative exists for y on 1 to 7. What's my justification going to be when they ask me, hey, do we meet these preconditions? I'm going to say yes, because y is continuous on 1 to 7 and differentiable on 1 to 7. Now, I don't know that I need to actually show any work. Like, I don't know that I need to take this, set this equal to 0. No, find out if this is undefined somewhere. I don't think I actually have to get to that level of justification. I think I just have to claim these things. Okay? Second question. Second question is find x equals c such that, remember what the mean value theorem says. The mean value theorem says if f is continuous on the closed interval and differentiable on the open interval, then there must be at least one point, and we call that point x equals c, such that f prime of c equals f of b minus f of a over b minus a. All right, so I need to find the slope of the secant, and I need to set the derivative equal to the slope of the secant so I can find this point. All right, well, let's start by finding the slope of the secant. This means I'm supposed to plug in 7 and 1 into this f function. 7, 1. So f of 7, 49 minus 21 is 28, plus 1 is 29. And f of 1, 1 plus 1 is 2, 2 minus 3 is negative 1 over 6. So this is going to be 30 over 6 or 5. I want f prime. I'm wondering when f prime equals 5. So I'm going to take f prime and set f prime equal to 5. So f prime was 2x minus 3 equal to 5. So x equals 8 and x equals 4. That's the place. The tangent line to this parabola at this point has the same slope as the slope between 1 and 7 on this parabola. Said a different way, parabola from 1 to 7, slope equals 5, and here at x equals 4, the slope of the tangent is also 5. This tangent line and secant line will be parallel in places where the mean value theorem is true, because this slope and this slope are the same. Okay, and so yes, you're going to need to be able to deal with the mean value theorem. And so here's one for you. Y equals x over x squared plus 4, and we're looking on the interval from 1 to 4. All right, same questions. First question, does this on that interval meet the preconditions for the mean value theorem? And then second, if it does, you want to satisfy our curiosity to where that happens. Okay. No, there are no vertical asymptotes here, you're right. And that's kind of cool, because we know then that f prime will never be undefined. But really, pause the video and give it a go. Do we meet the preconditions? And secondly, find C if we do meet the preconditions. All right. So what I know about this is that this function is continuous, and certainly on 1 to 4. I mean, if you're not sure, you can always graph. Pass through 0, 0. We've got no vertical asymptote. The degree here is less than the degree here, so I got this going on. And if I put in a positive number for x, I'm going to get a positive value, like 1 over 5. But this has to come back down again. And likewise here, if I plug in a negative 1, I'm going to have negative 1 over 5. And so I'm going to have something like this. And I don't know, negative 1. I don't know if these are the max. They're just, yeah. I could use my calculus to find where the maxes and mins are, but this isn't that problem. This problem is the one saying, did we meet the preconditions in order to use NVT? And look, this function and if only we're looking over here from 1 to 4, this function is certainly continuous on 1 to 4. What about differentiable on 1 to 4? Well, do you see any undefined slopes here? I see a bunch of negative slopes on my drawing. Let's algebraically take a look at slopes here for a second. Okay, so this is either quotient rule or chain rule with a product. I think I'm going to do it this way. Y prime is x times, bring that down, -1, x squared plus 4, don't forget to subtract 1, times the derivative in here, 2x, plus this, x squared plus 4 to the -1, times the derivative of that. Okay, I'm going to factor out the smallest power, and that's going to be x squared plus 4 to the -2, and what's left over? Well, I've got a negative x times 2x, that's negative 2x squared. And then I've got this plus sign, and I factored a negative 2 here. And so that's going to give me x squared plus 4. Yeah. So then what becomes of this? Well, this is going to be negative x squared plus 4 on top, and here, x squared plus 4 squared on the bottom. There's my y prime. And no, really, you don't have to write it this way. This is fine. But I just wanted to say, look, I would set this equal to 0 to find when y prime was undefined. This is never equal to 0. Look, think about it graphically. It's a freaking parabola, shifted up 4 places. Don't even worry about that. Does this ever become y equals 0? Does this ever cross the x-axis? No. This is never equal to 0. So stop worrying about y prime undefined. Y prime is, though, equal to 0. When I set this numerator equal to 0, I get x equals plus and minus 2. So I've got 2 critical values here. There's -2, there's +2. These are places where y prime is 0. And if I do some testing around here, well, yeah, I agree. See, we're only looking at 1 to 4. So I don't really need to look over here. 1, 4. So I want to plug in 1, and I get -1 plus 4 is 3 on top, and a positive number on the bottom. Positive over positive is positive. And then 2 to 4. Sure, let's plug in a 3. 3 squared is 9, minus 9 plus 4 is -5 over, I'm always positive. I get a negative here. And so what's happening at x equals 2? Oh, there's a max. But wait, what were we doing in this problem? All we're trying to do right now is answer the question, does this stupid thing meet the preconditions for MVT on that interval? Was this function continuous on 1 to 4? Yes, we are continuous on 1 to 4. Is this function differentiable on 1 to 4? Did you find any places where the derivative would be undefined on 1 to 4? Well, there are no places where the derivative is undefined. So we know that y is also differentiable on 1 to 4. So yes, we meet the MVT preconditions. Great. And since we meet the preconditions for MVT, that means we're supposed to go further, and we're supposed to say, okay, satisfy our curiosity. Where does y prime equal f of 4 minus f of 1 over 4 minus 1? Right? The slope of the secant on the original graph needs to equal the slope of the tangent at a single point. In order to figure this out, I need f of 4, which means I'm plugging 4 into these x's. 4 squared is 16 plus 4 is 20. 4 over 20 is 1/5 minus f of 1. 1 plus 4 is 5. I get 1. Whoa! Over 3. And so I get 0. Oh, isn't that nifty? We're looking for a place where y prime is equal to 0 because the slope of the secant is 0 on 1 to 4. Therefore, where does y prime equal 0? We already figured that out. Okay, so, and if we hadn't figured that out, what I'd be doing now is saying I'm supposed to set this slope, 0, equal to y prime. Here's y prime, negative x squared plus 4 over x squared plus 4 squared. Okay, so the first thing I do is I multiply both sides by x squared plus 4 squared, right? Because that takes those away. 0 times stuff, that's gone away. And I get negative x squared plus 4 equals 0. And I got x equals plus and minus 2. So, are you going to tell me that there are two values of c where the mean value theorem works? And we're going to say, well, actually, no, because we're only looking on that interval. And therefore, negative 2 is garbage. We had already thought about that when we found out when y prime was equal to 0 and made our sign chart for it. But, you know, that's one of those things that people often don't think about. Like, they do all this great calculus, and they get the plus and minus, and then they forget to realize that we're only looking on this interval, and so negative 2 couldn't exist. Wow. All right, so I want to look at one last thing with you today. But really, wow, these are such great test questions. Given that f prime of negative 1 equals f prime of 1 equals 0, and f prime is greater than 0 on negative 1 to 1, union 1 to infinity, oops, 1 to infinity, and f prime is less than 0 on negative infinity to negative 1. And what we'd like here, we also know that f of 0 equals 4. We want a continuous function. We want a continuous function. Can we draw a continuous function based on this information? Okay, so let's start with that f prime sign chart. It looks like negative 1 and 1 will have slopes on f of 0. F prime of negative 1 is 0, and f prime of positive 1 is 0. Okay. Now, f prime is greater than 0 on this interval, and for this interval, f prime is less than 0 on this interval. So what can we say is happening? Well, I know when f prime goes from negative to positive that I have a minimum. So f has a min at x equals negative 1. Now, I also have a 0 slope here on f, and f is going from increasing, 0 slope, to increasing. Increasing, 0 slope, to increasing. And that's going to be x equals 1. X equals negative 1. I've got a minimum at negative 1. Okay. Is f, since f prime is negative up to negative 1, that means that f is decreasing until we get to negative 1. Sure, I got that. And then I see f should be increasing from negative 1 to 1. And then after 1, f is increasing again. I have a horizontal tangent here. It's a little easier to see up a flat space. And a horizontal tangent here at negative 1. Don't forget, f of 0 needs to equal 4. So that place is 0, 4. And there's my graph of f. I would have felt more comfortable if I had some information about concavity, but I feel pretty confident about this because I want a continuous function. Kind of also want a differentiable function like that. That's not differentiable at negative 1, right? My slopes are approaching negative infinity from the side my slopes are approaching 0. The limit of the slopes from both sides? No, that doesn't exist there. So that derivative doesn't exist, but we were told that f prime of negative 1 does exist and is equal to 0. So we're not going to have any funky stuff like that. We're just going to have plain old, it's going to be like this. Okay, well, I think that's a fabulous amount for you to be chewing on with this video. And I hope you're really comfortable with it.